Hello friends, we were discussing about the equilibrium transformations. Okay, we were seeing that in equilibrium condition under eutectic phase diagram also, that how the microstructures will come out. In that, now today's lecture I will try to discuss about solidification structures, basically how the solidification structures are going to be present in a material. Okay, and also we will see the non-equilibrium, how the non-equilibrium transformation will takes place if I am doing under non-equilibrium condition. Okay, because earlier we only discussed about the equilibrium condition in eutectic phase diagram. This time we will discuss under non-equilibrium condition, and we would like to give a little bit of mathematical treatment to that. Okay, so till now we were only discussing qualitatively that okay, these microstructures will be there. Now we will also try to give a mathematical treatment to that. Okay, and from there we would like to bring a very important structure, okay, that I will tell you in the next slide. So basically we will discuss three cases here, and these are equilibrium solidification, no diffusion in solid but perfect mixing in liquid. So in the liquid portion we will keep doing some through stirring process some mixing. Okay, and in the solid it will be there will not be any diffusion. So no diffusion means why we are saying no diffusion, because we are going to do cooling very fast. So we are not giving enough time for solute atom to diffuse in the solid. The third case will be again no diffusion in solid, and in the liquid also the mixing is diffusional. Okay, so these will be the three cases, and you will see in the slide some very nice microstructures are there. Okay, so first microstructure if you see, okay, this is a pro-eutectic phase. So you can see this as a pro-eutectic phase which is there. Okay, and in between a pro-eutectic phase, these are the eutectic microstructures. So you can see a dark phase and the bright phase, okay, together. And in the pro-eutectic phase also you can see that effect of coring. If you remember, we discussed about solidification coring. Okay, so you can see the gradient in the composition starting from the where the first solid which has started forming. Okay, and as it is going away from that center. Okay, you can also see that this the pro-eutectic phase which is formed, it has some nice shape here. That shape you can see from another angle, like you can see that there are some branches which are coming. So there is a main branch and some other branches. Okay, another one you can see here very nicely. Okay, so you have a main branch coming, and then there are side branches which are coming. So it looks like a dendrite. Dendrite is a tree like Latin word where when we say dendrite, it looks like a tree. So you have a main branch, then you have other sub branches and some more tertiary branches and so on. Okay, so you have this primary branch, then you are getting these secondary branches, and there may be some tertiary branches also can be formed. So this type of structure is called dendritic structure. Okay, or these are called dendrites, and this is a very typical microstructure you will see in a cast material where solidification is taking place under non-equilibrium condition. Okay, so and you can see that there is a large variation in the microstructure, and of course there will be compositional variation also. So you have all these dendrite. These are all pro-eutectic phases, and then between two dendrites you have a interdendritic region which is a eutectic phase. Okay, so all these things we have to take care in the subsequent processing. So for any material, the first condition is that you do melting, pour the molten metal into some ingots or cast whatever cast mold you have prepared. Okay, and then in that it will do there will be a solidification. During solidification you might have this kind of dendritic structure. between dendrites you will have interdendritic structure, okay, and there will be large compositional variation and this kind of microstructure. Now this microstructure is not a good microstructure from material property, for material properties, mechanical properties basically. So we have to get rid of this microstructure in the subsequent processing. So if you remember, for one processing already we have discussed, which is called homogenization. So homogenization we will try to at least homogenize the composition throughout the ingot, and with other processing, for example rolling or extrusion or forging, we would like to break this dendritic structure, okay, and maybe try to get some fine recrystallized microstructure. So these microstructure we will see subsequently, okay. So this is the idea. So this we want to understand, and for that this lecture is, okay. So to define variation in the solute content in the solid and the liquid, okay, we will define a term called partition fraction, okay, which is given by we are saying that it is K, the partition fraction is K, and which is the mole fraction of S divided by mole fraction or weight fraction of L, okay. So if you are talking in terms of weight fraction, it can be weight fraction. So or if you are talking in terms of moles, it will be mole fraction of solute in solid XS and mole fraction of solute in liquid XL, okay. So as you can see here in the diagram here, okay. So we have a material for which we have kept overall composition as X naught, okay, and we are starting the solidification from some temperature in which it is fully liquid, and when it crosses this temperature T1 here, okay, and when it crosses this liquidus line at T1, okay, the solidification will start, okay. So the first solid which is going to form, okay, you already know we can plot a tie line wherever it is cutting the solidus curve, that will be the composition of the solid, okay. So this is the first solid to form, okay. So at this my liquid is, it is totally liquid. So my liquid has the composition of X naught. So what will be the composition of solid at this point, okay. So I can just say that if this is K equal to XS and XL is the overall liquid which has a composition of X naught here. So I can put XL as X naught here right now at this condition, which gives me the composition of XS as K into X naught, okay. So that is what is written here. Then we will go to some temperature T2, okay. At T2 you have some solid which has composition of XS and some liquid which has composition of XL, okay. So you can see that as the solids are forming with much lower solute content, my solute content of liquid is increasing. I am actually rejecting this much solute in the liquid when a solid is forming, okay. That is how I can form. So my initial composition is X naught. So I have to reject this much solute content in the liquid, okay. So that is why the composition or the solute content of liquid is increasing. So you can see this graph is going like this. So initially the liquid has a composition of X naught, but with the progress of solidification the solute content in liquid is increasing, okay. And at T3 temperature where my composition is crossing the solidus line here, okay, I will have solid. Now the total solid is of X naught composition, okay. This whole thing is going under equilibrium condition right now, and my liquid will be having, okay, similar expression again, because the total solid has composition of X naught. So my liquid will have composition of X naught by K. So at XS I will put X naught and this will be XL. So XL will go here, K will come here, so it will be X naught by K. So last liquid which is going to be there in the or last droplet of liquid which is going to be there in the system, okay, it will have a composition of x naught by k. Okay. So, that is I will represent here. So, this is a very kind of a nice experiment people have done. Okay. So, you start with a bar like this, okay, and this you fill the liquid, okay, and you have an insulation around it. Okay. So, you have insulation around it, okay, and you are allowing heat to be extracted only from this end. Okay. So, initially it is fully liquid. So, because I am allowing liquid to heat to be taken out only from one end, the solid will start forming from this end, okay, and it will keep on there is a progressive increase in the solid content and the whole liquid will transform to solid at some point. Okay. So, we can now see, because solid is growing only from one side, I can see that how the composition is changing at different temperatures. Okay. So, initially at T1 temperature, as I told you, the composition of solid or solute content will be this, which is given by kx naught, and liquid will have x naught composition. Let us see what happens at T2 temperature in this particular volume in terms of solute content. So, on the x axis we have solute content, okay, and on y axis we have the distance from the end from which the solidification has started. Okay. So, at T temperature the solid will have overall composition will be xs, which is given by this phase diagram. The solute content in the liquid, okay, so this is my solid, this is my liquid. So, solute content in the liquid will be given by xl, okay, which is given here, okay, and the overall composition is x naught. So, at different temperatures the solute content in liquid and solid will keep on changing, okay, till at the end of it the whole solid will solidify with the composition of x naught throughout the volume of the this particular cast material. Okay. So, this is under equilibrium condition. Okay. So, you can see that in the overall solid the composition is same, in the whole liquid the composition is same. Okay. So, there is not going to be any compositional variation when you are doing under equilibrium condition, which is not the case in normal practice, because to do this I have to do this solidification very slowly. Okay. So, we will see what happens in the non-equilibrium condition. So, first condition we are taking is no diffusion in solid and perfect mixing in liquid. Okay. So, rate of cooling has to be much faster, because I am not allowing any diffusion to take place, and composition of liquid is homogeneous. That is why we are ensuring by putting a stirrer in the liquid. Okay. So, whatever solute is rejected from the solid, it will be uniformly distributed throughout the liquid. Okay. So, now what will happen to my phase diagram if we do under non-equilibrium condition? Okay. So, whatever is there under non-equilibrium condition in the phase diagram are usually shown with a dashed line like is shown here. Okay. And why we are going to get this? Okay. Let me explain you. You can see that at the first, when the solid is forming, it is forming with a composition which is given by kx naught. Okay. X naught is my overall composition. Okay. At temperature T2, okay, now my again if I take the same experiment, okay, again I have done insulation here. Okay. So, there is no heat taking out from here, heat is only taking out from this end. So, solid is forming. So, the first solid which is going to form, okay, let me show by a very thin layer here, okay, and plot it. Okay. This will have a composition of kx naught. Okay. Now, slowly it is progressing. Now, my the system is coming from T1 temperature to T2. Okay. So, what will happen now, the same story will be repeated for every temperature in between T1 and T2. Okay. So, at T2 temperature, let us say what will happen is that my composition of the solid is excess, which is more than the kx naught. Okay, so let us plot some more lines here. So, at this point now my composition is excess, okay, and now it started from kx naught and I am not allowing any diffusion to take place, and now the composition is excess. Okay. That means there is a composition gradient from this end to this end, the solute content is increasing. So, if I want to give an average composition for whole of this solid, okay, which I am going to call as excess bar, okay, that will be much lower than what is given by the phase diagram under equilibrium condition. So, this point is shifting from this excess to this here. Okay. Let me show it here. Okay. So, at temperature T2 now, okay, the composition is not excess for the throughout the solid. The composition is some new composition which is an average composition which is excess bar. Same thing will keep on repeating, okay, and what will happen that progressively my solid has a lower composition than given by the phase diagram, okay, and you can also understand that if in equilibrium condition it should have composition, throughout composition should be excess, but it is much lower than that. That means I am enriching the liquid by that much amount of solute. Okay. So, liquid concentration will keep on increasing. Okay. So, you can see that this graph, instead of going like this, okay, it is continuously increasing and it is the graph is coming like this, and where the eutectic reaction or isotherm of the eutectic temperature is there, at that point the remaining liquid which is increasing, the solute content of remaining liquid is continuously increasing and reaching the eutectic composition. Okay. So, the remaining last part of the liquid, okay, so my solid will keep on growing, okay, with a lower composition than what is given by that, okay, and the last part of the liquid will transform with a eutectic composition. Okay. So, always in a non-equilibrium condition, okay, though my composition is not going to show, under equilibrium condition is not going to show any eutectic because it is in single phase, but because of the non-equilibrium cooling I am always going to get some eutectic mixture in the material. Okay. A very important thing is there to remember. Okay. So, again composition profile, if we want to see at different temperatures. So, composition profile just under T1, okay, just when the solidification has started. So, my solid has composition of Kx naught, my liquid has composition of x naught, okay, the overall composition. At temperature T2, the first solid which has formed has composition of Kx naught, and now because I am not allowing any diffusion to take place, the composition is increasing, and at T2, okay, at the interface the composition is excess and the composition overall is given by XL, okay, the composition of the liquid, and because we are doing stirring, the composition profile here is constant. The composition profile at the temperature T eutectic and below, okay, T is your eutectic temperature. Okay. So, what will happen, the composition in the solid is increasing from Kx naught, okay, and slowly it will cross the x naught composition, okay, and then suddenly it will increase and go up to Kx max, which is given by this, okay, this is my x max, and the remaining liquid, last part of the liquid will transform with the composition of eutectic composition. Okay. So, this is how the composition or the solute profile will be there in the solid at the end of the solidification. Okay. Now, I can also give a mathematical kind of analysis for this this problem here. Okay. So, what is the variation of excess along the bar? So, what we are saying is that solute rejected in liquid, okay, when a small amount of solid forms, okay. So, when a small amount of solid forms, which is given by dFs, okay. So, this is my small amount of solid which is forming, and what will be the solute rejected okay, there is always going to be some solute which is rejected when solid is forming, and that will be equal to, this is the composition of liquid from which I am forming this solid. So, this much amount of liquid has to be rejected in the liquid, then only I can form the solid of excess composition. So, I am forming a solid of excess composition from a composition of liquid which is given by XL. So, I have to reject this much solute, okay, whenever a small amount of solid is forming into liquid. Okay. So, that is what we are saying here. So, XL minus excess amount of solute has to be rejected when I am forming a small amount of solid, and with the resulting increase in solute in liquid. Okay. So, the liquid fraction will be given by FL. Okay. So, when I am forming a small amount of solid, the remaining FL, the fraction of liquid, will be enriched by that much amount of solute. Okay. So, increase in solute in liquid will be this much. So, FL I can write as 1 minus Fs dxl. Okay. So, now if we do a little bit rearrangement here, XL or XS I can replace again here. For example, XS I can replace as KXL, okay, or I can say it as KXL I can say. Okay. So, this will become XL minus KXL into TFS is equal to 1 minus Fs dxl. Okay. And XL can be taken out here. So, it will be XL 1 minus K dFs is equal to 1 minus Fs dxl. Okay. And I can do another rearrangement here. So, it will be 1 minus K dFs upon 1 minus Fs is equal to dxl upon xl. Okay. And now, if we integrate on both the sides, okay. So, I will integrate it from 0 to 1 or 0 to Fs, okay, and this I am integrating from xl to x naught. Okay. So, when I integrate this, okay, and after doing the integration, the solution will be like this. Okay. So, it will be xs equal to k x naught 1 minus Fs to the power k minus 1. Okay. And this is actually what we call as non-equilibrium lever rule or Scheele's equations. Okay. So, under non-equilibrium condition, this you can consider as a lever rule which tells me about the fractions and their compositions. Okay. So, using this you can be able to find out what will be the composition of solid, okay, for a given fraction of solid, okay, knowing the partition fraction. Okay. So, I can use this equation under non-equilibrium condition. Okay. So, this is my now mathematical representation of a non-equilibrium cooling. Okay. Now, the third condition is no diffusion in solid and diffusional mixing in liquid. So, solute rejected from solid will be transported by diffusion in liquid. Okay. So, you can see that in this case now my first solid is forming again with Kx naught composition and the solute content is increasing, and in the liquid now you can see the composition is not constant throughout, okay, because the solute will build up at the interface and the solute is taken away from the interface by diffusion process. Okay. So, again there is an exponential curve here, okay, through which through diffusion it is taken out. Okay. At T3 constant velocity, at a constant velocity V, steady state will be reached at T3 temperature. Okay. The T3 temperature I can just show you which T3 temperature we are talking about. So, from here to here it will be a non-steady state condition. At when the system reaches a temperature T3, you will reach the steady state condition. So, this will be an initial transient, okay, from when the composition in solid is increasing from k x naught to the composition x naught, okay, which you can see from here. So, now my solid is forming at the composition of x naught, okay. So, starting from k x naught, the solid has reached the composition of x naught here, okay. So, solid is forming a x naught composition, the composition in the liquid at the interface is equal to x naught by k. So, that you can see here. So, composition at the liquid will be equal to, if I again draw a tie line here, okay. So, this will be my composition and it will be equal to, if this is x naught, okay, again if I use my partition fraction. So, xs is at x naught, okay. So, xl will become x naught by k, okay. So, that is what we are saying here at the interface x naught by k, and away from the interface, okay, at some point the liquid will have the composition of x naught. So, some solute is rejected, that solute will diffuse in the liquid by a diffusion process, and we can define this that what will be the slope of this curve, okay, by a characteristic width here, which is called, which is equal to diffusion coefficient of solute in the liquid divided by v velocity, okay, velocity with which my interface is moving. So, at the end of the solidification, you will see this kind of concentration gradient in the solid bar, okay. So, at the from where the solidification is starting, you will have k x naught composition, then the steady state will come where the whole solid will have a composition of x naught, okay, and then the final transient will be there, where again whatever solute I am rejecting in the material, that will build up, okay, and when this d by v reaches the last part of the bar, okay, the remaining liquid will the composition will rise suddenly to the eutectic composition, and the remaining liquid will transform with a eutectic composition. Okay, so this is how the variation of solute content will be there in the solid. Okay. Now, we will do a further analysis that what is happening in the liquid. Okay. If you see in the liquid, the solute content is varying like this in exponential curve. Okay. Now, if the solute content is varying like this, okay, you can see that as the solute content varies in the phase diagram, okay. See, you can understand it like this. If my solute overall solute content of a alloy is this, then the melting point is given by this. If my solute content is this, then melting point is given at a lower melting point. If solute content is this, then my melting point will be this. So, my melting point of my alloy keeps changing with the solute content in the liquid. Okay, that much we can understand from this graph, that if my solute content is more, the liquid the melting point will be lower. As I am going toward the pure material, my liquid or melting point will keep on increasing. Okay. So, this is the effect of the solute content on the melting point. Okay. So, that we will use here to understand that my solute content in the liquid is changing like this. So, at this my solute content is equal to x naught by k. Away from the interface, the solute content is decreasing and it becoming x naught at some distance away from the interface. Now, if this is the variation in the solute content, there will be variation in the melting point of the material. Okay. So, my melting point of the material will vary like this. In the interface, the melting point is equal to the T3 temperature. Away from the interface, the melting point is T1. So, solute content is more, the melting point is less. As the solute content is coming down, my melting point is increasing. So, this can be a curve to show you the melting point of my solid my alloy of different solute content at different positions. Now, when I am taking out the heat from this bar, okay, I am actually superimposing a temperature gradient on that. Okay. So, you can see that there is a temperature gradient given by TL, okay, that temperature from where I am taking out heat, the temperature will be lower, inside the temperature is more. Okay. So, now if that temperature is lower than the melting point here, okay, what I am doing basically is I am doing a undercooling of the alloy. If my imposed temperature is lower than the melting point, that means I am doing an undercooling. So, you can see that some portion of my liquid is undercooled, okay, and if you are doing an undercooling, okay, then means there will be a driving force for phase transformation. Okay. So, the critical gradient will be given by, as you can see, if I plot a tangent for the solute curve here, it will be equal to d by v. Okay. So, my critical gradient will also be defined by that. I will plot a straight line from here, which will be d by v distance away from the interface. So, this is my critical gradient. If my critical gradient is more is lower than this, then you will have constitutional supercooling, okay, because it is because of the solute content, and if the critical gradient is more than that, then of course there is no harm and you will not have any problem in the solidification. So, when you have constitutional supercooling, we will see that what happens in the solidification structure. So, the critical gradient will be given by T1 minus T3, okay, basically y2 minus y1 divided by x2 minus x1. So, it will be T1 minus T3 divided by this distance, which is given by d by v. Okay. So, the necessary condition for forming a stable protrusion, there must exist a region of constitutional supercooling in the liquid, and my superimposed temperature gradient should be less than critical gradient. Okay. If I am not able to maintain this, okay, then what will happen is that I will have a condition where some material will be transforming at much faster rate, where the undercooling is taking place. Okay. So, this is what we call as the condition for the stable planar interface, that my critical gradient should be more than this. Okay. If it is lower than that, okay, then I will have what we call as this kind of breakdown in the planar interface. Okay. So, if the temperature gradient is more, then you will have a planar interface like this. If the temperature gradient is less than the critical gradient, then what will happen? You will start getting this kind of unstable region, okay, and I will call it as a protrusion. Protruding part is there, okay, and when protrusion is formed, okay, what it does it, because my solid will always have a lower solute content, okay, so it will eject the solute. So, all these arrows are showing that I am ejecting solute in the liquid. So, this is my liquid, this is my solid. Okay. So, I am ejecting solute here, and this solute will come and get deposited at the root of the protrusion, okay, and thereby when the, as I told you, when solute content is increasing, my liquid melting point will decrease. So, again you will see that this temperature is higher than the melting point. So, again some solid will again go into the liquid phase, okay, and by that what will happen is there will be a kind of a depression here on both the side, and that will trigger another protrusion. Okay. So, now a planar interface has become a interface which is like this, okay. It is called a cellular structure, which is shown in this micrographs also here, and the steps are shown here. So, first step is the formation of first protrusion causes solute to be rejected laterally and pile up at the root of the protrusion. This lowers the equilibrium temperature, causing recess to form. Eventually, protrusion develops into long arms or cell growing parallel to the direction of heat flow. The solute rejected from the solidifying liquid concentrates in the cell wall, which solidify at the lowest temperature. Okay. So, when you have this condition, okay, then sometime what will happen, that these will become planar interface, and these will also start developing protrusions like this. Okay. This will also start developing protrusion like this, and which will give you a dendritic microstructure. Okay. So, to get the dendritic microstructure, okay, I have to have a non-equilibrium cooling, okay, and I have to have a condition where the solute is rejected in the liquid under diffusional process, okay, and there has to be a constitutional supercooling or undercooling in the liquid phase, okay, to have this kind of unstable formation of the protrusion, okay, or unstable planar interface, okay, and then you will have secondary arms coming, and then you start getting the dendritic structure, and the liquid in between will get enriched in the solute content, and at the end of it the whole thing will transform by eutectic composition. Okay. So, you can understand that though we took a composition which is much lower, which is in the single phase of the eutectic also, okay, ultimately I am going to get some liquid which is transforming under eutectic composition. Okay. So, with this I will thank you, and we will this is a very important topic of understanding the structures which form under during solidification. Okay. Thank you.